Professor,
Yes.
it's Michelle. I have to go. I got my little ones here, and it's like an hour and a half drive back to my house.
All right. Do what you got to do.
All right, thank you. Are you recording this?
I just clicked record,
Okay.
so we should be all right.
All right, thank you. Have a good
Oh,
night.
Omar, can you hear me yet? Omar, he can't hear me. Ah, Omar, try your laptop.
He's almost out of battery, but we'll try to find a plug.
All right. How cute are her kids? Are they adorable?
Yeah, they're cute.
All right. Anyway, let's get some work done here. Okay. I'm just wasting time now. All right, so I'm going to go into assignment manager. Practice quiz 4. Preview practice quiz 4. All right, so I think there's 18 questions, 17 questions. All right, so this is going to be very challenging, folks. I'm going to try to teach you, this topic in 90 minutes. Fortunately, you have learning resources and things like that. All right, so when we're talking about probability, at the heart of talking about probability is ways to count things. All right, and I'll tell you what I mean by that. So there's something known as the law of total probability. All right, and the law of probability. This is something you've probably done in your head at some point. It's the number of outcomes favorable to an event happening divided by the total number of outcomes. And we can look at this in a very simple way. Like if I roll a 6-sided die and I want to find out what the probability of rolling a 2 is. Well, the number of outcomes favorable to rolling a 2 would be 1. There's only one way to roll a 2 on a 6-sided die. The total number of outcomes is 6. So the probability of rolling a 2 would be 1 out of 6. So this law of probability, this is the central theme of this entire chapter. However, it's not always easy to calculate the number of things, the total number of outcomes, right? So I'm just going to try to teach you as much as I can in the time that I have. So in this first, is this question number 1?
Mhm.
These must be shuffled. All right. So in a race in which 7 automobiles are entered and there are no ties, in how many ways can the first 3 finishers come in? All right. So I'll tell you what we're going to do. We're not going to do it this way. If I have to give you an extra section, I'll give you an extra section because we're skipping way, way, way too much, right? I can't jump into combinations without discussing anything else. So I'm going to go to problem set 7 instead. All right. So the fundamental counting principle. What does the fundamental counting principle say? Well, the fundamental counting principle says if there are n ways to do one thing and m ways to do a second thing, then the total number is m times n. All right, so what does that mean? So let's say you go to a restaurant, right? You go to a restaurant and they have 3 appetizers and 7 entrees. Just keep it simple, right? So what are the total number of options? Actually, let's do with one of these problems. All right. This way, I don't have to rephrase them or anything. We can just look at the problem. So you're taking a multiple choice test that has 7 questions. Each of the questions has 5 answer choices with 1 correct answer per question. If you select one of these choices for each question and leave nothing blank, in how many ways can you answer the questions, right? So this this counting principle, okay, the fundamental counting principle. So let's look at it a different way. Let's draw a picture. All right. So let's say I have a test. All right. And on this test, I have 1, 2, 3, 4, 5, 6, 7 questions. Right. Each question has 5 answer choices. So there's 5 ways that I could answer each one of these. So the counting principle states that you want to multiply these, right? So if there's 5 ways to answer the first question, and 5 ways to answer the second question, and 5 ways to answer the third, and so on and so forth, you want to multiply those together, right? So the answer to this question would be, in how many ways can you answer the questions? The answer would be 5 to the 7th power. And that makes sense, right?
Yeah.
Right. I think this is easier to understand when you just like put like blank spaces, right? 5 ways to answer the first one, 5 ways to answer the second one. Really, the thing to take away from the fundamental counting principle is the fact that you're multiplying things. You're not adding them. You're multiplying them. And let's see if we let's check our answers. Actually, I could just. This would save some time too. Hold on. I don't have enough face-to-face time with you, right? 4 out of 7 of our classes, we had to take a test. So they changed the question. If you're taking multiple choice tests, there's 5 questions. Each question has 4 possible answer choices. It's not 4 times 5. It's going to be 5 times, I'm sorry, 4 times 4 times 4 times 4 times 4, right? So that's going to be 4 to the 5th power. So I got 4 up, 5, enter. That's how they got 10, 20. But if you have to, just map it out, right? So you got 1, 2, 3, 4. We got 5 questions. And there's 4 ways to answer each one of these questions. So the total number of ways to answer a question will be 4 times 4 times 4 times 4 times 4. All right. Now, license plates. License plates in a particular state display 2 letters followed by 2 numbers. All right. So you can see, oh, dang. Can you see that?
Yes.
So we have a letter and a letter and a number and a number. All right. So how many different license plates can be manufactured for this state? Well, how many letters are there?
26.
26. How many letters are there? 26. How many numbers are there? 10. 10. So this is just 26 squared times 10 squared. 26 squared times 10 squared. It's 5,057 or
You put, I think, that 24 and 20 instead of 26.
oh, did I? You're right. 26 squared times 100. Yeah, 67,600. All right, let's look at the next one. A stock can go up, go down, or stay unchanged. How many different possibilities are there if you own 9 stocks, right? So if you wanted to, you've got 3 possibilities for the first stock, times 3 possibilities for the second, times 3 all the way out to the 9th one. It's just 3 to the 9th power. All right, so it's 19,683. Okay, now, so that's just a fundamental accounting principle, right? And now the next method that we learn is going to be permutations. We're going to learn about permutations and combinations, okay? And the big thing that we have to understand is with permutations, order is important. With combinations, order is not important. So what does that mean? Okay. Well, what it means is this. Anyone ever played a Powerball? So in the Powerball, there's 5 numbers that get picked from 1 to 69. And then the Powerball, I think there's, I forget, 32 options for the Powerball, right? But there's 5 numbers to get picked, 1 through 69. So order, not important. I got to remember that Omar can't hear, I don't think. Order, not important, means that A, B, C, and B, A, C are the same. Order important means that A, B, C, and B, A, C are different. So when you're doing permutations, there'll be way more permutations than there are combinations. So I'm just going to presume that everyone does not know what a factorial is.
Yeah, no.
Okay, so factorial is the number of ways to arrange things one at a time, right? So let's say I have a seating chart, right? I got 1, 2, 3. I got 4 seats in the front row right here, right? And then I got Omar coming in. I've got Weatherby coming in. I've got Michelle coming in. I got Kevin coming in, right? Omar gets there first. How many choices does Omar have?
4.
4, right? So Omar's going to sit right there. Omar's handled, all right? Now, Weatherby comes in second. How many choices does Weatherby have?
3.
3, okay? He doesn't like Omar very much. He's actually going to sit way over here, right? You're not friendly at all right? And now Michelle walks in. She's got 2 choices, right? So she's stuck with one of you. And then Kevin is always late, so he's got to sit there, right? All right. So this counting method, the number of different ways that 4 people can sit down is 4 times 3 times 2 times 1. That's a permutation, right? Because order does matter here, right? Order does matter here. So this is a permutation. So like, if let's say it's Thanksgiving dinner and you got the big table out, right? And you got it set up for 10 places because 10 people are going to come. Well, how many different ways can those 10 people sit in those 10 spots? And the answer is simple. 10 factorial. Right? It's really quite amazing. So now, this is where calculator math gets real important, right? So we're gonna be talking about we're gonna talk about three things on the calculator. We're gonna talk about n factorial. We're gonna talk about NCR, which means, can you see the bottom there?
Yes.
Which means n things taken R at a time. And then we're going to see NPR. This is combinations, right? So order is not important. And this is N things taken R at a time. And this is permutations. Okay, so you got to find this stuff on your calculator, right? Hopefully your calculator has a stat button or a math button, right? So on my calculator, I got a probability button, right? So if I wanted to find factorial, what I'm going to do, like let's say I wanted to find 10 factorial, I want to hit 10 first. Remember, this is going to be a huge number, right? I want to hit 10 first, and I hit my probability button. And you see the choices right here? Can you see these choices?
Yeah.
You see N, P, R, N, C, R, and factorial. Mm-hmm. That's all we're going to need for all these problems, right? Those three, NPR, NCR, and factorial, right? So I wanted to find 10 factorial, so I'm going to hit that. And notice how it says 10 factorial now?
Yeah.
Right? And I hit enter. That's how many different ways 10 people can arrange themselves around a Thanksgiving table with 10 seats. Right? What if we had two different tables? Right? What if we had two different tables? One table that held 6 people and one table that held 4 people, right? So if we're talking about the number of ways that 6 people can arrange themselves taken from a group of 10, right? I got 10 people trying. You don't want to sit at the little kids' table. Actually, that's totally untrue. I prefer to sit at the little kids' table. But if I've got 10 people trying to sit at the main table and they care who they sit next to. So in other words, order is important. Believe it or not, all we have to do to solve this problem is 10 permutations. You still see that?
Yeah.
What are the number of ways that 10 people can arrange themselves, or 6 people out of 10 can arrange themselves at a table? So let's look at a couple problems with permutations. There's lots of videos in media and stuff like that. Like, I hate to leave everybody hanging, but there's just not enough time for me to cover everything. But hopefully some of these basics will help you. We still have an hour and 3 minutes. Like, we still have significant time. So let's look at problem number 4. We have 7 performers who will present their comedy acts at a comedy club. One of the performers insists on being the last stand-up comic of the evening. If this performer's request is granted, how many different ways are there to schedule the appearances? So I'm just going to draw some little slots, right? 1, 2, can you see the top? Yeah. 1, 2, 3, 4, 5, 6, 7. So there's 7 performers. One of them wants to be the last one, right? So no matter how these other 6 are arranged, this always stays the same, right? The last comic will always be in that slot. How many different ways can you arrange these? Let's see who's on fire today.
Be 6 to the 6th power.
Remember that thing I just showed you?
Oh, 6 to the premier.
720.
So if we didn't care, did you say 720?
Yes.
That's correct. That's correct. It's 6 factorial,
6
Yes.
right? There's 6 ways to fill this. Then that one's full. Then 5. Then you got 4 options, 3 options, 2 options, 1. Nice job. All right. So, this is just a calculator problem. But let me show you something kind of interesting, right? You need to be able to do this in your calculator. And when you're like dividing like combinations and permutations, you might want to use parentheses, right? Just to be on the safe side. But look at this. We have 113 factorial over 111 factorial, right? Couldn't I rewrite 113 factorial as 113 times 112 times 111 factorial? Doesn't that make sense? Does that make sense?
Oh, you just got the 112 because it's in the middle.
Well, I mean, what is 113 factorial? It's 113 times 112 times 111 times 110 times 109 times 108, all the way down to 1.
Oh,
That's what 13 factorial means. Why did I write it like this? Because I've got 111 factorial in the denominator. Isn't 113 factorial just 113 times 112 times 111 factorial?
yeah.
Do you follow me?
Yeah.
Everyone follow me on that? Right? So wouldn't this whole thing just be equal to 113 times 112? They'll cancel out. Again, this is a calculator math problem. You're allowed to use calculators. I just want to show you a little bit of insight of how, if you didn't have a calculator, you could solve this pretty easily, right? 113 factorial is 113 times 112 times 111 factorial. Make sense?
Mhm.
You can rewrite it that way. All right, this is just a calculator math problem. It's 5 factorial. By the way, what is 5 factorial? That's 6 times 20, it's 120, right? 5 times 4 times 3 times 2, right?
Yeah. Yeah.
3 times 2 is 6, times 4 is 24, times 5 is 120.
That's correct.
All right. Now, 5 factorial divided by 3 factorial. Wouldn't that just be 20? Right? Couldn't I rewrite 5 factorial as 5 times 4 times 3 factorial? That makes sense? What is 5 factorial? 5 times 4 times 3 times 2. I'm not going to say times 1 every time. We know that it's times 1, right? But multiplying by 1 doesn't change anything, right?
Okay.
5 factorial is 5 times 4 times 3 times 2, right? 3 factorial is 3 times 2. Isn't 5 factorial just 5 times 4 times 3 factorial, right? They cancel out. This is equal to 20. All right, now I need everybody to grab a calculator and learn how to do this right now. So what this means is 7 permutations taken 4 at a time. So this is like saying we have 7 people trying to sit at a table with 4 seats, and order is important, right? Let's say the seats are progressively closer to further away from a stage, right? So the first seat is more desirable than the second, and second is more desirable than the third. Order is important. So what we need to do, did I lose Omar?
Yeah.
Like lose him for good?
I don't know.
He probably he can't hear anything, right?
Well, he said that he's almost out of battery, but he was gonna try to find a plug.
All right. Anyway, so I need to make sure that everybody here knows how to do this on their calculator. So, Kevin, do you have a probability button on your calculator?
Yeah, I bought the same one you have.
Okay, incredibly smart. Weatherby, do you know how to do this on your calculator?
No.
Do you want to bring your calculator over here so I can look at it?
Yeah. Do you think this one will work? I don't know if it has any other stuff.
No, unfortunately, this one does. Oh, wait a second. Yeah, you're good.
Really?
Yeah, got a probability button right there. Look, see, there's your 3 things.
Oh yeah.
NPR, NCR, factorial.
That's awesome.
Yeah.
Which
So-
one did you press to get that?
PRB, probability.
Oh,
We're in the probability section.
yeah.
That's a probability button,
That's perfect.
right? So for you to do 7P4, you're just going to go 7, hit the probability button, choose that one, and then hit 4, and then hit enter,
Dang, that's good.
right? So 7P4 would be a permutation, 7C4 would be a combination, and then you also have your factorial button. So yeah, you're in business.
Awesome.
All right, so for Kevin, we're going to go 7, then we're going to hit the probability button, and we have a permutation, so we're going to hit enter, and then we're going to hit 4, and then hit enter. Kevin, you good with that?
Yeah, I got it.
All right, cool. We don't have to spend a ton of time on that. By the way, 15P0, 15 things taken 0 at a time. What do you suppose that's equal to? How many ways can you take nothing?
0.
Well, I think you can take it 1, right? You take nothing, you reach into a bag and pull nothing out. There's only one way to do it, right?
One time.
So if my memory serves me, I know for a fact that I'm correct, right? It's Pascal's triangle. If I had more time, I would teach you Pascal's triangle, and you'd be amazed. All right, now look. One of the hardest parts about permutations and combinations is establishing whether order is or is not important. Because actually doing the math, you're not doing anything. The calculator's doing the math. So we have a club with 18 members, and they want to choose 3 officers: president, vice president, and secretary treasurer. Is order important?
Yes.
Yes. What if it said 3 committee members? Would order be important?
No.
No. Since these are ranked or different, we have a permutation. You're not going to believe how easy this is. Like, this is literally to solve question number 10. It's 18P3. That's it. That's all you got to do, right? So I'm going to go 18. I'm going to hit my probability button. Then I'm going to select permutations and then 3. I got 4896. There's 4,896 ways to do this.
That's crazy.
It is, right? It's because order is important. What if order wasn't important? We would divide out, all the ways that I can arrange those three people, which in this case would be 6 ways, right? But if I did 18 and then a combination, it would be, you're basically just dividing that number by 6. Be like 600, 816, right?
Yeah.
So there are way more permutations than are combinations. Because in a permutation, ABC, ACB, BAC, BCA, CBA, and CAB are all different. So those 3 letters have 6 different ways to be expressed, right? Permutations will tend to be pretty big numbers, right? Now, next question. At a benefit concert, 7 bands have volunteered to perform, but we only have enough time for 5 of the bands to play. How many lineups are possible? So that word lineup suggests that order is important, right?
Mm.
Who's going on first? Who's going on second? Who's going on third? Who's going on fourth? When order is important, it's a permutation. This is just 7 choose 5. Or 7 permutations 5, right? So, well, that would be what, 42? 7 times 6. Oh, wait, hold on a second. Yeah. 7 permutations, 5, enter. 20, I was getting confused with combinations. 25, 20, right?
Mhm.
So that's all you have to do. Figure out whether it's a permutation or a combination, and then plug it into the calculator. What did I say, 2,520?
Yes.
All right. And how many distinct ways can the letters of the word states be arranged? All right, so this is a little trickier. This is a different type of problem. I think I have in my notes. Let's see if I can't. I have this written out for you somewhere. I thought I had it. Hold on.
Wouldn't it just be 120? Or am I
No.
wrong?
No, and I'm going to show you why. Oh, here we go. It's right here. So, why did you say 120?
Because the S is twice, so it would just be 5. Then the exclamation point. But I could.
Okay, you're thinking like a statistician, actually. That's interesting, right? So we have repeats, right? And that's what this section is called, repeated values. All right, so we have 1, 2, 3, 4, 5, 6 letters, right? How many different ways can I arrange 6 unique letters? That would just be 6 factorial, right? Let me, even though I'm on a different page, let me just write this out right here. So I've got 1, can you see the bottom?
Yeah.
I got 1, 2, 3, 4, 5, 6. So if I just had like A, B, C, D, E, F, that would be 6 factorial, right?
Mhm.
But I've got 2 S's, 2 T's, 1 A, and 1 E, right? So if I place A here and E here, that's different than E here and A there. You follow me?
Yeah.
But if I place S there and S there, well, that's not different from S there and S there. So we actually have to divide out the number of ways that S can be arranged, because we're not talking about A and E anymore, right? I've got S and S. So this would be 6 factorial. If these are all different letters, this is where it starts getting a little complicated, right? If it were all different letters, all 6 of these were different letters, it'd be 6 factorial. In fact, I'm going to do something a little crazy here, right? Let's change this to the word states, right? So we're going to have 3 S's. So we're going to change this to the word states. Hold on. I'll put an extra S on there. Okay. States with an extra S. So now I have 3 S's, 2 T's. So 1, 2, 3, 4, 5, 6, 7. So this whole thing can be arranged in 7 factorial ways. But if S was 3 different letters, if it was ABC, there'd be 6 different ways I could arrange those 3 letters. ABC, ACB, BAC, BCA, CAB, CBA, right? There would be 3 factorial ways I can arrange those 3 letters. But we don't have 3 different letters anymore. We have 1 letter 3 times. So those 3 factorial ways that I counted into the original permutation, they have to be divided out. Those 2 factorial ways that I can arrange the T's, they have to be divided out, right? So this would end up being, all right, so the original question, the reason I wanted to do 3 factorial, so you can see different numbers, right? But if we have the word state, how many different ways could we arrange state? Well, how many different, or states? Well, how many different ways could we arrange A, B, C, D, E, F? That would be equal to 6 factorial, right?
Yeah.
Because every one of those things is being permuted, right? But since I have 2 S's, well, those 2 S's aren't going to be changing places. The 2 S's in 2 slots, no matter what 2 slots they are, they have to, it doesn't matter. It's still the same. If I have S in 1 and 4, that's the same as S in 1 and 4. So I have to divide out all those doubles, right? And then I've got 2 T's. So I have to divide out all those doubles as well. So believe it or not, the answer to this would be 6 factorial divided by 2 factorial times 2 factorial, which would be 6 factorial divided by 4. So 6 probability factorial, enter, divided by 4, enter, that's 180. So when you have these repeats, you got to divide them out, because we're not flipping them around. We're not flipping the 2 S's around. This is a great question. So obviously we're synced up to where I was when I did the homework earlier, right? Question 13. So I'll do the one that they have, right? I'll leave this open to that page, but I'll do the one that they have. All right. So a signal can be formed by running different colored flags up a pole, one above the other. Find the number of different signals consisting of 8 flags that can be made using 4 white flags, right? So now it's a little bit more obvious why the 4 factorial white flags has to be divided out. If I got 1, 2, 4 white flags up at the top, there's no way to permute those. The 4 white flags up top is 4 white flags up top, right? So I have to divide that 4 factorial ways that I would have, arranged them had they been all different colors. I'm going to divide that out. So we have 8 flags, right? If we have 8 flags and they're all different colors, there's 8 factorial ways to arrange them.
Scoot it down a little bit, would you?
Yeah. So if we have 8 flags, there's 8 factorial ways to arrange them, right? Everyone get that?
Yeah.
Kev, you get that?
Yeah, I'm tracking.
All right. So, but 4 white, 2 red, 2 blue. I've got 4 white, 2 red, and 2 blue. Well, I mean, there's white, 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 white is the same thing as white, 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 white. So those 4 factorial, if they were different, that needs to be divided out. So I'm going to divide out 4 factorial, 2 factorial, and 2 factorial. Because all those permutations aren't going to happen when we have repeats. Does that make sense?
Yeah.
This is one of the trickier things in the section. Does that make sense?
Yeah, that makes sense.
Yep. Yeah.
Okay, cool. I mean, if you get that, that's great progress. So I'm going to go 8 probability, go down to my factorial. Oh, you can't see that. Go down to my factorial button, right? And I'm going to divide by, but now I'm going to use parentheses because I'm going to have 4 factorial. Listen, 2 factorials too, right?
Yeah.
There are 420 ways to do it. And I'm sure back in the day before we had, social media and cell phones and, it was the Renaissance and people were trying to attack your castles. I'm sure having 420 different messages that can be sent by arranging flags could be very valuable.
Yeah.
Right? This stuff is cool. This is my favorite thing in all mathematics by a lot. This is a field of mathematics known as combinatorics. And let me tell you something. If you're good at combinatorics, you can make a handsome living. So that's permutations. Combinations can get way more complicated, but only because now we can have a discussion about permutations and combinations, right? So now, but in a previous section, we knew the order was important in all the problems. Once we introduce combinations, now we have to decide whether order is important or it's not. Like, for instance, a medical researcher needs 18 people to test a drug. If 46 people volunteer for the test, how many ways can 18 people be selected? Is order important?
No.
No. This is a combination. You with me?
Yeah. Because it doesn't matter what order they come in. It just needs 18 people.
We just need 18 people, right? In fact, it's going to be a double-blind placebo test. It couldn't matter less, right? How many different 5-letter passwords can be formed from the letters A, B, C, D, E, F, and G if no repetition of letters is allowed? All right. Is order important here?
Order?
Is ABC different from BAC?
Yes.
Anyone own a bicycle?
Yeah, I do.
Do you have a lock for that bike?
Yeah, it's like it has the letters.
Yeah. Know what that type of lock is called? It's called a combination lock. Do you know that that is absolutely wrong? It's a permutation lock. It is not a combination lock. The name of a lock is wrong, right? Because if your password to open your lock is 1, 2, 3, 4, and someone enters 4, 3, 2, 1, it's not going to open the lock. Your lock is a permutation,
Yeah.
not a combination, right? You know, by the way, Kevin, Weatherby just got out of the jail in Nashville. Wasn't sure if you knew about that. Got himself into a pickle. All right, so here, yeah, order is
Attaboy.
definitely important. Nah, I'm kidding. I did actually have a student 2 semesters ago that got locked up in a Mexican prison. He actually sent me an email, and he's like, "Hey, I'm not going to be there this week because I'm in a Mexican prison." And as it turns out, it was true.
What do you do?
He went hunting in Baja, Mexico, and the person that wasn't even in the party, they had one letter wrong on their hunting tag, and they collected up everybody that was in the convoy and put them in jail until they sorted out that one person's license.
Oh my gosh.
Mm-hmm. You're carrying rifles
Yeah.
into Mexico.
Yeah, it makes sense.
Okay, right? All right. So use the formula. Well, you don't have to use the formula, right? I'm not even teaching you formula. I don't have time. You know how to do this on your calculator, right? But think about this for a second. 827, right? Let's put that in our calculator. 8, and then I'm gonna go, oh snap. I'm gonna go 8, and then probability, and now I'm gonna go down to number 2, and then hit 7, right? So 827. Doesn't that kind of make sense that it would be 8, right? Like, order's not important. So I'm selecting 7 from 8. So to think like a statistician, each time I'm omitting one person, right? Each time I'm omitting one person. How many different ways can I omit one person when order isn't important? 8. I'm choosing 7 from 8 every time a different person is being omitted, right? I love this. This, like I said, one of my favorite things in all of mathematics.
So if you forgot a combination on your bike lock and it had like 5 letters, that would be a permutation. So you just do 5 permutation, and then what would you do after that?
Oh, okay. So you wouldn't even go that far because we're not selecting
Yeah.
a smaller group from a larger group. It would just be 5 factorial.
Oh wow. So it's how
Oh, no. No, hold on. You're talking about combination. All right. What are you really talking about here? So let's say you have a combination lock, which should be called a permutation lock, right?
Uh-huh.
This is a fundamental counting principle problem, right? You got 1, 2, 3, 4, 5 numbers on your lock, right? Each one of these goes from 0 to 10 or 0 to 9, right? So how many different ways? How many different combinations are there? 10 to the 5th power,
Oh wow.
right? And that 10 to the 5th power is just 10 with 5 zeros. There's 100,000. So there's 100,000 different ways you could have a combination on a lock that has numbers and 5 different slots.
You'd have to try 100,000 times.
Correct.
Oh my gosh.
Well, think about this. Well, what if you knew somebody's phone number, right? You remember their last 4 digits, but you can't remember their first 3, right? So you got their phone number, you know their 305 area code, and you know their last 4 digits are 1474, right? You can't remember the first 3. How many different ways? How many different numbers would you have to try?
It goes up to 9.
Well, 0 to 9 is 10 numbers.
Yeah, 0 to 9.
Just because 1 to 10 is 10 numbers, right? 0 to 9 is 10 numbers. So like say 1 to 10.
It's a 10 to the 3rd power.
Yeah. You'd have to try 1,000 numbers. Right? 10 to the third power. That's the fundamental counting principle, right? There's 10 ways to do the first one. There's 10 ways to do the second one. There's 10 ways to do the third one. There's 1,000 different numbers that you would have to try just to get those first three. By the way, I've got 19 and I'm choosing 19. How many ways can I choose 19 where order isn't important out of 19? Think about it for a second.
19 out of 19.
Order's not important.
So 19 combination 19.
Uh-huh.
This is one.
It's one. There's only one way to choose 19 people out of 19 people.
Are we not in order? Yeah, that makes sense.
Yeah,
It's tricky.
it is tricky. But once you get it, it's glorious, right? It's actually worth spending some time learning. 6, choose 0. How many different ways can you choose 0? One.
One time.
One way. All right. So listen, this is just a math problem. Make sure you get the right answers on these, though. If you have to, use parentheses, right? If you have to, do something like this. I've got 11, choose 7, right? I'm going to hit enter, right? I'm afraid that it's going to divide 7 by something. I'm not even sure that's true. But 11, choose 7, and then divide it by 3, choose 2. I'm using, well, we know that 3, choose 2 would be 3, right?
Yeah.
How many different ways can you choose 2 from 3? You're omitting one person 3 different ways, right? But we'll go 3, probability, choose 2, and then enter. This is 110.
Nice.
This stuff is fun. It is. This is my favorite part of this whole class. I was psyched when I was looking at the competencies, and if I teach this class again, I'm going to figure out a way for me to spend way more time teaching this and maybe skimp out on something else, like set theory or algebra, right? So an election ballot asks voters to select 6 city commissioners from a group of 12. Okay, they're commissioners. There's no ranking. There's no presidents. How many ways can this be done? 12, choose 6. Just 12, choose 6. 924 ways. There's about 4 or 5 of these questions on your final, by the way. I'd much rather encounter this than a future value problem. All right. To win at Lotto in one state, one must correctly select 6 numbers from a collection of 65 numbers. 1 through 65. The order in which the selection is made does not matter. It's just 65, choose 6. Don't get confused that the word lotto has double letters in it. It's not the same type of problem, right? This just, we're choosing 6 numbers from 65 numbers, and order is not important. So this is 65, choose 6, 82598880. 82598880. 82598880. How easy is that? How many ways can a committee of 5 Democrats and 6 Republicans be formed from a group of 8 Democrats and 6 Republicans? This is where it starts getting tricky. This is where it starts getting tricky, right? So, question 22. I need a committee of 5 Democrats and 6 Republicans. And I'm forming it from a group of 8 Democrats. Oh, well.
Divided by that?
Well, I'm going to show you. All right. Wouldn't 6 choose 6 just be 1? Only one way that can happen. All right. So I've got I've got 8 Democrats and 8 Republicans. I want to form a committee that has, hold on a second. I'm sorry, I have 6 Republicans, 8 Democrats and 6 Republicans. I want to form a committee that has 5 Democrats and 6 Republicans. Committee has 5 Democrats and 6 Republicans, right? This word "and" is a very important word in the world of probability. The word "and" always means multiply. So we're actually using the fundamental counting principle and we're using combinations in this problem. So how many different ways, let's handle this like 2 different problems. How many different ways can I pick 5 Democrats from 8 Democrats? Say choose 5, right?
Yeah.
How many different ways can I pick 6 Republicans from 6 Republicans? It's 6, oh, sorry. It's 6 choose 6 or 1, right? We know that's 1, right? So this would be 8 choose 5 times 6 choose 6. We know 6 choose 6 is 1. So we'll just do 8 choose 5. There's 56 ways to do this. It's almost unbelievable that this works, right? All right. The Senate in a certain state has 60 Republicans, 36 Democrats, and 4 independents. So the Senate has 60 Republicans, 36 Democrats, and 4 independents. All right. How many committees can be formed if each committee must have 3 Republicans and 2 Democrats? Right? So this would just be 60. We need 3 Republicans and 2 Democrats. This would just be 60 choose 3 times 36 choose 2. That's it. 60 choose 3, enter, times, I'm just going to use parentheses because this scares me. 36 choose 2, 21558600.
Big number.
That's a big number. 21558600, enter. And that's why these counting methods are so important, right? Well, you're not going to sit down and write this out by hand. You say, okay, so we got Fred and Linda and Jack in this one. This one, we got Fred and Linda and Susan. This one, we got Linda and Susan and Paul. Like, it would be impossible to do that by hand. But combinatorics takes care of all of it, right? And makes it, quite frankly, easy. Now we get to that problem that we were looking at the practice test, right? We got a race. 11 automobiles are entered. How many different ways can the first 3 finishers come in? Is order important?
Yes.
Yes. First place is better than third place, right? So all we do here is 11P3. Is it crazy that that's that easy?
Yeah. Just plug and play it.
It's just 11P3. We figure out whether order is important or it's not important. Now these get harder, and I don't have time. Like normally I would do the harder questions and forget about this stuff, right? But you can't. You need this foundation to understand the harder problems. I can't jump into a problem like this before talking about the fundamental counting principle, before talking about combinations, and before talking about permutations. Now that we've had that talk, you at least have the foundation where you could do some of these like probability problems. All right, we still got 23 minutes left. So let's see what we can get done. 11P3, so that's 11. I'm gonna hit my probability button. There's 990 different ways. That's a crazy big number. All right, on to the next section. So we've actually just blown through 2 entire sections of probability, right? Now,
This is good.
oh man, dice problems and card problems. This is my bread and butter, right? You know, you don't want to go to the casino with me. All right. Actually, I probably haven't been to a casino in 10 years. I don't gamble. You know why I don't gamble? I'm a statistician.
Do you know
They call it what do statisticians call it? They call it stupidity tax. Right? Playing the lottery, stupidity tax. Right? You ever heard of the law of large numbers? Okay, so I'm going to teach you the law of large numbers real quick. If I flip a coin 3 times, would it be that weird for me to get 3 heads in a row?
No.
No. In fact, there's a 1 in 8 chance, 12.5% chance of that happening, right? If I flip a coin 100 times in a row and I get 100 heads, are you going to look at the coin to see if it's got heads on both sides or what?
See if it's weighted.
See if it's weighted, right? There's no way that's going to happen. The probability of that happening is 1 over 2 to the 100th power, right? There's no way that's going to happen, right? The law of large numbers, and we're going to talk about empirical probability, theoretical probability. I'm giving you the crash course. This is like learn probability in 45 minutes. That's what I'm giving you today, right? Like I'm going to make a YouTube video. So theoretical probability, okay? What theoretical probability is, it's a known probability, right? We know that the probability of getting a 6 on a 6-sided die is 1 out of 6, right? We're not collecting any data. We're not doing any calculations. We know that there's one way to get a 6 on a 6-sided die. The probability is 1 out of 6, right? Empirical probability. What does empirical probability mean? Okay, well, empirical, the word empirical means based on data, right? Based on observations. Empirical literally means observations, right? So, let's say I was running a little beverage stand at a soccer game, right? And I bought a case of soda, I bought a case of water, and I bought a case of Gatorade, right? If I sell 10 sodas and 20 waters and 30 Gatorades, I have collected data. So based on that, if I sold 10 sodas, 20 waters, and 30 Gatorades, well, what is the probability that the next thing I sell is going to be a water? Well, I've sold 10, and what does this add up to total?
That's 60, yeah.
10 out of 60. So that's the probability.
1 out of 6.
So that's the difference between theoretical probability, and it is just merely an accident that it's 1/6 again. But that's the difference between empirical probability and theoretical probability. It's very, very simple things to calculate. Gets much harder further down the road. All right, so if I have a 12-sided die, what is the probability of rolling a 7?
1 in 12.
1 in 12. All right. So, there's something else I want to talk to you about, even though I'm getting kind of order, right? Kind of out of order. So, with limited time, this is very important to talk about. The word and, the word or, and the word not. Okay? So the word and, whenever you see that, it means multiply. And it also means that that more than one thing has to happen. Right? You can't draw a king and a 7 if you only draw one card. The word "and," there has to be more than one event, right? But could I draw a king or a 7?
Yeah.
Yeah. Can't draw them both unless I draw twice, right? The word "or" means add. And the word "not" is 1 minus the probability that it happened. All right. So this is incredibly important. We'll get to this in just a second, right? And means multiply, or means add. Not, you just subtract the probability of the thing happening from 1 to get the probability that it didn't happen. I remember I went to a Wawa. I'm from PA, so Wawa's the thing. There's none of them down here.
Yeah.
Right? So I went to a Wawa one day. I was on my way to the laundromat and I needed $8 in quarters. Right? So I asked the girl at the counter if she'd give me $8 in quarters. And she said, sure. So she opened up a new roll of quarters, cracked it open, started counting. 1, 2, 3, 4, 5, 6, 7, 8. Once she hit 8, I yelled, stop. And she's like, why? I'm like, because I need $8 in quarters. And she's like, I've only counted 8 quarters. I said, yes, you've counted $2 out of a roll of $10 worth of quarters. What's left? And she said $8. I'm like, we're done here. Right? That's what a complement is, right? If the probability that someone thinks that cash will be obsolete in 20 years is 0.18, then the probability someone doesn't think that is going to be 1 minus 0.18. Does that make sense?
Yeah.
Make sense? Right? If the probability someone is a vegetarian is remember, probability is always a number between 0 and 1. If you say 10%, that's not a probability, that's a percent. Right? Probability is always a number between 0 and 1. So if you say that somebody, there's a 10% chance that the next person that walks into this building is a vegetarian, well, what's the probability that they're a vegetarian? It'd be 0.10. So if the probability that someone who walks through the door is vegetarian, what's the probability that they're not a vegetarian? If it's 0.10 that they are, what is it?
It would be 99.
No, it'd be 0.90. 10% versus 90%, right?
Yeah.
It's 1 minus 0.10,
Yeah.
right? So the probability of something happening and the plus the probability of something not happening equals 1. Always. If
Yeah,
those,
one is 100, pretty much.
what's that?
Like 1 is basically 100.
Correct. One is 100. We learned that 2 weeks ago, right? When we were talking about decimals to percentages. How do you get a decimal, turn it into a percentage? You move the decimal place to the right.
Yeah.
A probability of 0.35 means that there's a 35% chance of that thing happening. Make sense?
Yeah.
All right. So what is the probability of rolling a number less than 1? We can use this idea of a complement, right? Or less than 12. So the probability of a number that's less than 12 on a 12-sided die, well, that would be equal to 1 minus the probability of 12, right? Less than 12 would be 1 through 11.
Yeah.
So 1 through 11, the probability of 1 through 11 plus the probability of 12 equals all the probability, all possible outcomes, right? So, I mean, we can just say this is 11 out of 12, right? But we can also use this idea of a complement. So this would just be the probability of getting a 12 is 1/12. So the probability of not getting a 12 is 11/12. Make sense?
Yeah.
A real important concept. It is oftentimes way easier to figure out what the probability of something not being is. All right, look at this one. You're dealt one card from a standard 52 card deck. What is the probability of being dealt a 7? How many 7s are in the deck? By the way, here's a picture of a deck, just in case you're not familiar.
There's 4.
Right? Many people aren't. Okay? You'd be surprised how many people don't know the details of the 52 card deck. I've been teaching this forever, and when I start teaching cards, I have to have pictures. Right? So, what's the probability of being dealt a 7?
1 out of 4.
52.
4 out of 52. And now reduce it. It's got to be simplified.
Oh, 1 in 13.
1 in 13. Bang. Easy peasy, lemon squeezy. All right. What's the probability of being dealt a club?
4 out of, or 1 in 13 again.
No. How many clubs are in the deck?
Oh, there are.
How many suits are there?
There's 11.
How many suits are there?
4 suits.
Okay. So how many out of 4 is clubs? We got clubs, diamonds, spades, and hearts. There's 4 suits. Clubs is one of them. What's my answer?
Would it be 13 divided by 52?
Yeah, yes, but guys, there's 4 suits. They all have the same amount of cards, right?
Oh, so 1 in 4.
Clubs is one of the 4. What's the probability of being dealt a club? 1 out of 4. Right?
Yeah.
Now, ultimately, there's 13 clubs out of 52 cards. If you reduce that, you end up with 1 out of 4. But think about it. There's 4 suits. The probability of being dealt a club is 1 out of 4. Make sense?
Yeah.
All right. What's the probability of being dealt a jack of hearts?
It's 1 out of 52.
1 out of 52. There's only one of them in the deck. All right. What's the probability of being dealt a 7 and a 10? Okay, they're saying you're dealt 1 card. Can you be a 7 and a 10 at the same time?
No.
No. All right, but now let's talk about. We only got 10 minutes left, so I'm going to go off the rails a little bit here. All right, so let's see if you can see my paper here. All right, so back to this idea of and or not. What is the probability of being dealt a 7 let me write it differently. What's the probability of being dealt a 7 and a queen? This gets tricky, right?
Mm.
Right. First question you got to ask yourself: are you putting the card back? Right. That's the difference between conditional probability and not conditional. Right. So let's say we're putting the card back. We're going to say with replacement. So what is the probability of drawing a 7?
4 out of 52.
And if we reduce that, it's what?
2 out of 13.
Or 1 out of 13, right? No, 4 to 52. Yeah, 1 out of 13. 52 divided by 4 is 13. 4 divided by 4 is 1. So it'll be 1 out of 13.
Yeah.
Right? What's the probability of drawing a queen?
The same thing.
Same thing. 1 out of 13. And the word and means what?
Add.
Read it again.
Multiply.
The word and means multiply. the probability of drawing 2 cards with replacement and getting a 7 and a queen, right, would be 1/13 times 1/13. What if I didn't put the card back, right? So let's take a look at without replacement. And I'm going to show you the trickiest thing in this whole section after that. So without replacement, what is the probability that I'll draw 7? Okay, we got full 52 cards. What's the probability I'll draw 7?
1/13.
1 in 13. Now one of the 7s is out of the deck.
So not 51.
What's the probability I'm going to draw a queen now?
1 in 51?
Not 1. How many queens are left?
Oh, 4. 4 in 51.
You see?
Mhm.
Now, the trickiest part about this is the word and. When things are disjoint, right? Like if I ask you, what is the probability of drawing, let's switch gears from and to or, right? What if I ask you the probability of drawing a queen or a 7? Let's take a step back because this is already complicated, right? What about if I just ask you the probability of grabbing an 8 or a 7? Can 8 and 7 be on the same card at the same time?
No.
No. So that means that the probability of drawing an 8 and the probability of drawing a 7, those are disjoint. They are not mutually inclusive. They are mutually exclusive, right? Can't draw the 8 of 7s. So what would this probability, so what's the probability of drawing an 8?
1 in 13.
1 in 13. What is the probability of drawing a 7?
It's the same thing, 1 in 13.
1 in 13. And the word or means what?
Add.
Add. Probability of grabbing an 8 or a 7 is equal to 1/13 plus 1/13. These are disjoint. There is no overlap, right? But, and this is the thing that gets you, right? What is the probability of drawing a queen or a 7? Let's see if you can figure this one out.
Would it not be the same thing?
Okay, this will be the same thing, right? Now, what about probability of drawing a queen or a heart? What's probability of drawing a queen?
1 in 13.
I'm going to leave it with a 52
Yeah.
this time, right?
4 in 52.
All right. What's the probability of drawing a heart?
11.
13, right?
The 13. Sorry.
Are these disjoint?
No, because there is a heart queen.
Yeah, that's correct. These are not disjoint because there's a queen of hearts. So don't the 4 out of 52 include the queen of hearts?
Yeah.
And doesn't the 13 out of 52 include the queen of hearts?
Is -1.
We got subtracted out, right? And now, probability of 2 events, A and B,
Ooh.
right? So this is equal to, or sorry, I wanted to do or. So the probability of, we learned this in set theory, right? Remember the unit symbol, the union symbol?
Mhm.
The probability of A or, remember that means or, is equal to the probability of A plus the probability of B minus the intersection. You got to subtract out what they have in common. Let's see if I can find one of them real quick. We've got 3 minutes left. So this is pretty easy, right? A single die is rolled twice. You got 36 equally likely outcomes are shown. What's the probability of getting two numbers whose sum is 6? Well, you just look at where the sum of 6 is, right? Sum of 6, we've got 5, 1, 4, 2, 3, 3, 2, 4, 1, 5. So there's 6 ways you can get a sum of 6 out of 36. 6 out of 36 is 1 6. Hold on. Oh, duh. 6 has got 5 ways. 7 is the one it's got. All right. So I'm going to skip this because this is really simple. Skip. These are easy. You're just dividing things on a chart. We already did something like this, right? All right, now we're starting to get into stuff we've already done. It's 9 o'clock. So the last thing I want to tell you is this, okay? You see where it says get more help?
Mhm.
All right. You see where it says ask my instructor? Let me move this out of the way. See where it says ask my instructor?
Oh, just kick me out of the Wi-Fi. Okay.
All right, so if you click get more help, if you're working on a problem, you click ask my instructor, it'll link me to the problem you're working on.
All right.
So you're going to get stuck on some of these problems. I already know this to be true. If you get stuck, just use ask my instructor. I'm about to give finals. I actually already gave a final today. So I'm about to give finals in all 5 of my classes. So by Friday this week, my semester at the other college is over, right? I will have tons of time. So just if you get stuck, reach out to me. I'll be happy to help. All right.
All right.
Thanks, boss.
All right, man. We'll see you next week for the final.
Oh, wow.
Yes, sir.
Crazy.
It is crazy, right?
It came fast.